classify problems based on their running time. All right. So back in Euclid's day, he was credited with coming up with the first algorithm, which was for GCD, which I don't know how the pyramids were built when they didn't have any algorithms before this, but okay. So back then they said there are algorithms that we know and there are algorithms that we don't know, right? And then Turing came along, and his PhD advisor was von Neumann, and asked, can everything be computed? Does everything have an algorithm, right? And Turing proved that the halting problem, well, first he had to define formally what computation was, right? Gödel had a definition, but it turned out not to compute everything. And so Turing's machine was the first that computed everything we consider computable. And he proved halting problem is not in there, right? And then about the time I was born, this is me, this is my father, he said, computers were just being thought about. And he differentiated between polytime and exponential time. All right. And so let's look at our various classical time complexities. All right. The first is constant time. What's constant time? Is the running time is bounded. It doesn't depend on the size of the input, right? Like those stack operations, push, pop, their running time doesn't depend on how big the queue is, right? Constant time. Log n time, you take n, you divide it by 2, you divide it by 2. What can you do in log n time? What kind of search? Binary search, right? Binary search. Just last exam on 3101, I asked, give me an algorithm that has this running time and this running time. It's amazing how many people, maybe they memorized this algorithm has this running time, but when I said, give me an algorithm that has this running time, they panicked. All right, linear. What can you do in linear time? Yeah, the size of the input is n. So it takes linear time just to look at the input, right? If you look at each of the input items about a constant number of times, then that's order n time, right? And there's any problem like, let's say you want to add two numbers together. Can you add faster than linear time? Can you add two numbers together without having looked at it? No, you got to look at it. Maybe I can do binary search without looking at the whole thing. Maybe I can pop something off the top of the stack without looking at the whole thing. But you can't look at the whole thing, right? So if you need to look at the entire input, you got linear time at least, right? N log n is what? Your fast sorting algorithms, right? N squared time. Well, recursion is pretty broad, but sort of your slow sorting algorithms, right? You take your input this way, your input this way, and you compare and you fill out the matrix, right? It's if you have to look, if you're sorting and you take every pair of numbers and compare them, that's n squared time, right? Polynomial time, right, which my dad defined, is into some constant, right? And what's really true in life is that all but maybe a couple weird exceptions, if you come up with a polynomial time algorithm, the C is not bigger than 2 or 3, right? I mean, why would it be 10 to n to the 10? I mean, I don't know why that, I couldn't come up with an algorithm that's n to the 10 time. All right. And this is what we consider, if we partition between what we consider to be a feasible algorithm and an infeasible algorithm, these ones are considered feasible, right? Then there's a big jump up to exponential time, right? The algorithm that you guys did last question, the last three questions, what's their running time? It's exponential, right? If you talk about, if I have a set, how many subsets are there? I include this, I don't include this, I include this, I don't include this. It's kind of brute force. It's looking at all possible solutions, right? Then you have what is computable and not, which mathematicians, may still think about. And then you have uncomputable, right? Everybody get these classes? It's more or less what we're doing. Yeah. That was a long time ago. That was like in 93, and I don't remember. Don't remember. But it was kind of the beginning of quantum computing, and that was something I was doing at the time. And so I don't know. You look at every subset, and then I don't know. I don't remember. All right. So running time, right? Here we're plotting time versus work, right? No, sorry, input size. Input size versus running time. So that's constant, right? That's log n, linear, n squared, exponential, right? Here's a little table where we have the various running times and various input sizes, right? And you can see that even n squared gets a little scary, right? N cubed, right? It's not too weird nowadays to have an input of size 10,000, right? Hell, a photograph is a couple megabytes, right? So you can kind of ask, even on today's computer, if my file's a couple megabytes, what can I do? I can do linear. Well, maybe I could do n log n, right? Probably could, but you're not going to do quadratic time on a megabyte, right? You're certainly not going to, right? This is too much, right? Or here already, you're getting up to the size of the universe, right? Everybody good with this? Catch my little joke. My father's bigger than human. That was a father joke. All right. Now we can also think about calculus, right? Taking the derivatives of things. All right. Suppose I tell you that t is the running time for input of size n, right? Then if I increase the input, make it one bigger, how much bigger does the running time get, right? And if I double the size of the input, how much bigger does the running time get? I think it's useful to know, right? So what about 5? It clearly, yeah, right? Oh, here I guess linear, it goes up by 1 and it doubles, right? This one clearly doesn't change, right? N squared, if you make it 1 bigger, you go from n squared to n plus 1 squared. It increases by 2n. It's right? Here's the math. It's the derivative. It increases by 2n, right? It's the derivative of n squared, right? But if you double it, then what does the input do? Yeah. Yes, exactly. Right? So it goes up by 4. Right? Everybody see that? Because you go from n squared to 2n squared, right? You're going up by a factor of 4. All right. What about exponential? Do you make it 1 bigger? You're going from 2 to the n to 2 to the n plus 1. It yeah, it doubles, right? The time doubles. Every time you make your input 1 bigger, your time doubles. What about this? It's a little harder. You square the time, right? You double the size of your input. You do damage. It takes a lot longer, right? Log n, it goes up. If you double it, it goes up by 1. And the others are all they're kind of weirder, right? Everybody good? Yeah. 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 But these things here are giving you the relationship between input size and running time, right? So the question is, if I increase the input, let's say you have an input this big and you run it and it takes you a minute. Now I'm saying, if I make your input 1 bigger, what is it going to do to me? If I double the size of the input, what is it going to do to me? Right? Yeah. Yeah. So yeah, it's comparing T of n to T of 2n. Right? And or this one is comparing T of n to 2 of n plus 1, which feels like a derivative. I don't know if you're up enough on derivatives, but right? Derivative is your incremental cost, right? If I have an input of size n, it costs me this, right? Now I have an increment 1 bigger, right? Then I increase by the derivative, my next cost. Right? When I'm doing my taxes, for example, not only do I want to know how much taxes do I pay, but I also want to know, if I paid an extra $1, how much does my taxes increase? Yeah, here at 4. You're putting here 4 n squared? Yeah. Yeah, but I'm saying, here's an experiment. I give you an input of some size, you run it, has this much running time. All right. So you know n and you know t, right? Maybe you don't know this, right? But you know n and you know t. How big will the running time be when you go up to n plus 1 or 2n? Right? I'm just saying, what's the damage when you make your input a little bit bigger? Right? Yeah. Yeah. I mean, one thing about a constant, why don't we care about big O? Is because somewhat, if I put a constant in front of all of these, it won't change this picture. Right? All right. Let's have some appreciation for exponential time. Anybody want to guess what 2 to the 60 is? Anybody know? Right? This is how I would do it. I would say 2 to the 10. I know 2 to the 10, right? So 2 to the 60 is 2 to the 10 to the 6. right? Well, what's 2 to the 10? It's basically 1,000, right? So I get 2 to the 18, right? Which is the age of the universe in seconds. All right. So now let's do log n. All right. Suppose n is the size of the universe in seconds, right? What's the log of that? What's the log of 2 to the 60? Can't quite hear you, but yeah, base 2. You're working too hard, dude. If the log is base 2, then the log is 60. Right? All right. Right. So it barely grows. Right? You could say a running time of the log n thing, you could safely say it was 60 because your input's never going to be bigger. Right? Right. So here are different